All right, let's get started. So today we're going to be talking about everything we understand about turbulence. I'm done. Okay, so about turbulence, there is actually it's a topic that's very difficult to understand. Okay, so and if you don't understand, you're in the same camp. So like there is a saying that a famous physicist was saying that when I die and see the God, I want to understand two things. Like one is I think something about difficult theory about quantum mechanics. The other was turbulence, and for the first one, he was very optimistic. So turbulence is something we know how to model, but like we don't really conceptually understand. And today I'm going to be talking about some of the stuff we are able to model what turbulence is and its effect to aerodynamics. And so let's actually start with a very simple scenario. Okay, so again, let's first consider the scenario where there is no pressure force, only viscous force. So this is a scenario I think is actually very most simplified scenario of what a shear layer is. So there are two flat plates. The bottom flat plate is stationary, and the top flat plate moves with the velocity v0. And the distance between the two flat plates is v. Okay, so no pressure force, but there is velocity difference, right? The fluid close to the top plate moves together with the top plate. The fluid close to the bottom plate stays stationary. As a result of that, the velocity changes continuously from the bottom to top. Okay, and if you draw a control volume, let's say a rectangular control volume, okay, you're gonna see that because there is no pressure force, the only force acting on that control volume is viscous forces. And as we have said, viscous forces act on the face only if the velocity changes when you travel across that face, right? By that reasoning, which are the two faces out of the four faces I'm drawing here that there is non-zero viscous force? Top and bottom, right? Yeah, so if you look at the left and right faces, if you travel across the face, the velocity doesn't change. So there is no viscous force. But on the top and bottom, if you travel in the direction normal to the face, you can see that velocity goes higher and lower, right? So velocity changes when you are crossing the top and bottom face. And also, if this is a steady state flow, then all the forces have to balance each other exactly, which means that viscous force on top and on bottom has to be exactly equal, right? That means mu times du, actually I use the vx here, dvx dy, the derivative of velocity multiplied with the viscosity, that's the force per unit area, right? And also the top and bottom has the same area because I'm drawing a box. So this has to be equal to a constant no matter if I'm looking at the top face or the bottom face. Agreed? And I can draw any kind of a similar control volume that starts with any y, ends with any different y. And that thing has to be the same constant, right, at any y. So this means that dvx dy has to be a constant. Okay? A derivative being constant means what? For the velocity profile. The velocity profile is basically this vx of y, right? So if the derivative is constant, that means what does the profile look like? It's a straight line, exactly. And we are going to see that that's true only if the viscosity is a constant. Okay, and we're going to go to the turbulent case, and we're going to see that in turbulent flows, there is what we call a turbulent viscosity that makes this viscosity not a constant anymore, and that is going to affect the velocity profile, making it doesn't look like a straight line at all. So if between these two places there are turbulent flows, the velocity profile is not going to be a straight line. It's going to be a very strange shape you're going to see later. Let's look at a slightly different case. Okay, in this case, we have both pressure and viscosity present. Okay, which means I'm going to have two flat plates again, but both are stationary. And then I'm pushing the fluid on one side, okay, with a high pressure, and this is the outlet, low pressure. Okay, so then there is a pressure gradient. So for now, let's assume this is long enough so that the pressure gradient is uniform. So I have a constant grad P, or dP dx. And the dP dx is a negative, right? So if dP dx is negative, the pressure force is minus dP dx, right? It then points towards the positive x direction. So that's the pressure force. Now, of course, if I draw a control volume here, the same kind of control volume. All right, now there are 4 different phases. It's very interesting because now on all of the 4 phases, I mean, we're ignoring the phase on these 2 directions because we're assuming the flow in this direction is uniform, right? So whatever happens on this phase is going to exactly balance what happens on that phase, right? So let's just not consider this. Now on these 4 phases, all of the 4 phases have some force. On 2 phases, there are pressure force. On 2 phases, there are viscous force. Okay. Again, if you look at the left and right phase, there is no viscous force because you are traveling in this direction, the velocity stays the same. On this bottom and top phases, there is viscosity, there is viscous force because as you go in the directions, the velocity changes, right? I mean, we know conceptually, we know intuitively, if you push a fluid inside a pipe, the velocity is going to go faster in the middle and slower near the walls, right? So the velocity is going to change as a function of y. But if you think about pressure force, okay, so I'm thinking about pressure being only a function of x. So if you think about the contour of pressure, the contour lines are like the straight vertical curves, okay? And in that case, the pressure on top and on bottom actually balance each other exactly. On top, the pressure force always points towards inside of the control volume, right? Normal to the control volume boundary. So top balance with bottom. But left does not balance with right. Because on the left there is higher pressure, on the right there is lower pressure. So the amount of force pushing the volume of fluid from the left towards the right is higher than the opposite force, right? In this case, the viscous force cannot balance each other exactly. They have to work together to balance the pressure force. All right, make sense? Okay, so I'm explaining the laminar case, and you then have to generalize later on to the turbulent case. So you have to understand before you come to the blackboard to work on the turbulent case. All right? Okay, so now how much is the pressure force? So let's imagine the height of this control volume is delta y, the length of this is delta x. Okay, and there is a delta z direction. So the pressure force is what? The pressure force is actually dP dx times delta x. That's how much pressure difference there is, right, between left and right. So again, pressure is force per unit area. So I have to multiply by area, which is delta y times delta z, right? That's how much pressure force there is on this control volume. Agreed? And it's pointing towards the right, okay? And that has to be balanced by the viscous force. Now, if you think about the viscous velocity profile like this, so let's consider the bottom phase first. Okay, so the bottom phase, if the velocity increases locally as a function of y here, which direction does the viscous force apply on this control volume? Exactly, towards this side, right? So viscous force always tries to bring the fluid towards the similar velocity. So if you look at this phase, if the velocity is lower, below or outside of the control volume, higher inside of the control volume, then the slower fluid outside of the control volume will try to bring the faster fluid inside the control volume to a slower speed. So the viscous force over here has to point towards this direction, right? Okay, which means on the bottom face, a positive dV dy is going to mean a negative viscous force. So minus mu times dV dy. That's only force per unit area. I have to multiply by the area of this face, which is not dy dz, but dx dz, right? All right. So that's at the bottom. So that's at, let's say this is y0, this is y1. So this is at y0. Now let's consider y1. At y1, the velocity actually decreases as a function of y, right? In this case, which direction is the viscous force? Huh? Okay, so if you look at the velocity profile here, is the flow outside of the control volume faster or slower? Slower, right? So it's going to try to also bring the control volume to a slower speed, right? Okay, so basically you look at across a face, is the velocity outside faster or slower? If the velocity outside is slower, it is trying to slow down the control volume. If outside of the control volume the flow is faster, it is going to be trying to accelerate the control volume. So here, a negative dV dy means a negative force, right? Which means I have to add mu times dV dy now at y1, again delta x delta z. That whole thing has to be equal to 0. All right? Okay, of course, let's actually just get rid of a bunch of things and make it, let me see, delta x delta y. Yeah, let me get rid of a few things and make it a nice equation. So first of all, delta z can be removed and delta x can be removed, right? And the first term is dp dx times delta y, and then plus, this is really mu times dv dy. I'm going to write like in similar to calculus, y1, y0. So that's the difference of dV dy between y1 and y0, right? So when you do calculus integral, it's the same notation. That's equal to 0, okay? And now let's actually again do a bit of calculus. Let's make delta y go to 0. And actually let's divide both sides by delta y. So let's divide the whole thing by delta y. Okay, delta y is y1 minus y0, right? So, and then make delta y goes to 0. So then on the first term, delta y just cancels. On the second term, the difference between two things divided by the difference in the coordinate, what is that? As we take the difference go to 0. That's derivative, right? Okay, so then what we get is the second derivative of v with respect to y. That's going to be equal to 0. Make sense? Okay. Now let's look at what we get. We said dp dx is a negative constant, right? So this guy has to be a positive constant, right? A second derivative of velocity being a positive constant. Am I doing that right? dp dx is oh, actually, this is this force has to be negative dp dx, right? Because we are looking at the pressure force that's pointing towards the x direction. So all of the dp dx term has to be negative. Sorry for that. Okay, so minus dp dx, that's a positive thing, which means the second derivative velocity has to be a negative constant. So what does it mean by a velocity profile, a function having a negative constant second derivative? It's a parabola that goes like that, right? And that coincides exactly with that profile, with both sides being 0, okay? And so if you know both sides of the function being 0, and you know the curvature of the parabola, you know exactly what the parabola is. And that's basically what you get from this. Yes? Conceptually, this is equal to 0 because of a force balance. So there are 4 forces, right? There is a pressure force on the left, a pressure force on the right. The difference between these 2 pressure forces is the first term, right? Because I have so this term is the delta P, right? The difference in the pressure. It doesn't matter what is the magnitude, only matters is the difference between left and right, okay? And then there are 2 forces on bottom and on top, and that are viscous forces. So this is the viscous force on the bottom, this is the viscous force on the top. So this is just purely a force balance between pressure and the viscous forces. And the rest is basically simplification and from here to here using calculus, right? Taking like infinitesimal control volume. Yes? Yeah, so first of all, this is clear, right? Because we have a negative pressure force, negative pressure gradient. So the pressure force acts always in like the negative grad P direction. And this term has a negative sign because, okay, so consider 2 cases. If the bottom of the control volume lies in the bottom half of the channel, then dV dy is positive, and the viscous force acts in the negative direction, right? Because the fluid on the outside of the control volume, further beneath it, is even slower than the fluid in the control volume. Then it is acting into the control volume as a negative force, trying to bring the control volume to its slower speed, right? On the other hand, if the bottom lies on the top half, then dV dy would be negative, right? So which means as you go towards a higher y, the velocity decreases. That means that dV dy is negative. In that case, outside of the fluid, further beneath it is actually faster. The force is trying to accelerate the control volume. In both cases, the force is in the opposite direction of dV dy, right? So that's why there is a negative sign. You can use a similar argument for the positive sign here. Basically, when dV dy is positive, the viscous force from the top trying to accelerate the control volume. When dV dy is negative, the viscous force at the top will try to decelerate the control volume. So that's how we figure out the sign. All right. Okay, so that's how we derive for the laminar case. Again, laminar case means the mu is constant. Okay, we derive that, okay, the fluid inside this channel looks like a parabola. And in this week's homework, you are going to be working on not a channel, but a pipe, like a cylindrical pipe. And you are also going to be using something similar to derive what the fluid looks like inside this pipe. Right, I mean the calculus is going to be a little bit different, but you are going to be reaching similar conclusions. Okay, so now after we understand the laminar case, let's actually figure out what turbulence is like. Okay, so let's actually first gain a little bit of intuition. As I said, there is very little conceptual understanding we can gain about turbulence, but like we can actually gain some intuition about it by like watching what it looks like. So this is a boundary layer after it basically gets tripped into turbulence. So here's laminar, here's tripped into turbulence. Okay, what you see is that there is, of course, unsteady flow, first of all, And the most prominent feature of the turbulence is mixing, right? When you see a small blob, if you keep tracing it, it's some of the blob goes, you can see some of the flow goes into the closer to the wall, and some of the flow moves away from the wall. So if you see a white puff coming out, so a white puff is always the flow from inside of the wall getting towards outside, and the dark patch would be a fluid that gets trapped in the innards of the boundary layer. So there is a lot of mixing going on in a turbulent boundary layer. So in some sense, there is actually a very analogous, so the mixing due to turbulence, due to movement of packages of flow that you can actually see, is actually very analogous to the origin of viscosity. So some of you, I don't know, like when you study physics, did you talk about the origin of viscosity? Where does viscosity come from? Does anybody know that? Why is there viscosity? Or why, for example, why is there heat conduction? Actually, the analogy between like laminar viscosity or what we call molecular viscosity and the turbulent viscosity is actually very analogous to the difference between conduction and convection in heat transfer. Okay, so does anybody know like what is the source of heat conduction? Like why does heat conduct? Okay, nobody talks about this? So okay, so no matter if it's heat conduction or viscosity, they are all from microscopic origins. So think about molecules, think about the scale of molecules. So molecules are always moving randomly, right? They are just small particles moving around and bumping into each other all the time. So heat is basically how fast these molecules are moving in average. So imagine you have a portion of air that's hotter and another portion of air that's slower. It just means the hotter air, the molecules are moving faster, the colder air, the molecules are moving slower, right? And as you can imagine, as the hotter air, faster molecules bump into each other, they actually transfer kinetic energy, right, into the slower moving air. So basically the air that's colder gets heated up, simply means they get collided and the molecules now are moving faster. Viscosity is very similar, except for instead of transferring of kinetic energy, it is transfer of momentum. So if you have a portion of air, so just to focus, for example, on a case like that. So if you have air that's moving faster on average, by the way, I said on average because the air in this patch of, the molecules in this patch of air are moving actually in random directions. But if you average their random direction, average their random speed, they average into this vector, right? While you average something closer to the wall, it is basically zero, right? Okay, now imagine the fluid, the particles, the molecules on the moving portion gets bumped. I mean, it travels in random directions, so some of them actually travels upwards. If they goes into the slower moving air, that transfers momentum into the slower moving air, right? That brings the patch of air that's slower moving to a slightly faster average speed. Okay? And what contributes to higher viscosity? Higher viscosity is contributed if each molecule, okay, have higher mass, right? So if I have higher mass, then as I travel into my neighboring regions, I bring more momentum. Also, viscosity is contributed by having higher speed. If I have higher speed, right, then there are more molecules moving back and forth, right, at a unit amount of time. Then there is more momentum transfer. Viscosity is also helped if a molecule travels at a longer distance before it is stopped or bumped by another molecule. Because then it can transfer, for example, if a molecule can go all the way from here at a higher speed all the way to here, and then bump into something, then it can transfer a much higher velocity difference on average, right? So basically, the mass, the velocity, and the distance, in the molecular sense, is the mean free distance of the molecules. They all contribute positively to velocity, to viscosity. So, if you figure out, why can't I? Okay, so if you figure out what is the, remember, like we said, a viscous forces tau is equal to mu du dy, right? So if you look at what is the unit of this, what is the unit of viscosity mu, you can figure out the unit by dividing the unit of tau, which is Newton per meter squared, right, by the unit of velocity gradient, which is meter per second, then divided by meter, so that's basically 1/second, right? So what is the unit of viscosity? If you divide this, it is Newton per meter squared, then divided by 1/second, which is times second. All right. And now what is Newton? Newton is, what is a Newton? Yes, kilogram meter per second squared, right? Okay, and then if you multiply them together, what you're gonna get is kilogram, 1 over kilogram meter second, like that, right? Okay. All right. So this can be also written like this. So this can be written as kilogram per meter cubed. So that's a unit of density. Okay. So basically, let me just write it out. Times meter per second and times another meter. So essentially, viscosity is contributed by three things. One is how much mass of molecules are there in a unit amount of space. The more stuff there is in a unit amount of space, the more potent are the molecules able to transfer momentum, right? And this is speed. The faster the molecules are moving, there are more molecules moving across the unit interface and transfer momentum to the neighboring volumes. And the further away, the third one is distance. The further away the molecules can move, right? The more momentum they can transfer per unit time. All right. So this is with molecules. With turbulence, it's pretty much the same, except that what is working to transfer the momentum is not individual molecules, but patches of fluid. So if you look at, if you look at this, the patch of fluid, they go from higher speed regions to lower speed regions, and some of them comes out from lower speed regions to higher speed regions. Actually, see all of these kind of vertical rotating structures. They are all indications of what does it mean by rotate, right? Rotate means higher fluid gets rotated into slower fluid, getting slowed down, and then slowed down fluid then comes out and gets sped up. This is the transfer of momentum. And for a turbulent flow, the transfer of momentum is actually can be a lot more potent than the laminar, than the molecular motions, simply because of the distance is much larger. Okay, the velocity is a lot slower, but sometimes it's not that much slower, right? So the molecular motions is on the same order of magnitude, actually several times larger than the speed of sound. So the molecular motions has maybe like 1,000 or so meters per second, and in a turbulent flow, I mean, depends on the velocity. This may be like 10 meters per second. So something like 100 times slower. But the distance for turbulent flow is much larger. The average length of travel for molecules is actually very small, right? It's a small fraction of a micrometer in air. And for turbulent flow, if you look at especially large-scale turbulence, this can be actually as large as you want. I mean, like if you look at the atmospheric turbulence, the scale, the range of motion of fluid mixing with each other can easily be like hundreds of meters, right, in atmosphere. For airplanes, basically, it is essentially the thickness of the entire boundary layer. Okay, so essentially the main difference between laminar flow and the turbulent flow is how much viscosity there is. And in particular, if you look at a turbulent boundary layer, the distance a fluid particle can travel actually depends crucially on how far away it is from the wall. If a fluid particle over here cannot go that much, if you look at the small whirl or eddy over here, it can only rotate, it cannot rotate into the wall. But if you look at an eddy over here, it has much larger range of motion. And as a result of that, the turbulent, the resulting viscosity, I'm going to skip this, the resulting viscosity is actually a strong function of how far away I am from the wall. So let me just take a look again. Yeah, so this is a computational visualization rather than a experimental visualization of what a turbulent boundary layer is. And these are all kinds of structures like one can actually simulate, reproduce in a computer, observe in an experiment. But in terms of conceptual understanding of like why it looks like this, not much. All right. Okay. So let's actually do a bunch of exercise. The two figures is what I derived earlier in class, showing the velocity profile for laminar flow. Now consider turbulent flow. And here we assume that, by the way, this is a very common model of what turbulence flow looks like. Basically, I'm adding an additional viscosity to the original laminar viscosity. So mu is the viscosity for air. You can look up on tables. But for turbulent viscosity is actually not a function of the material. It's not a function of air, but a function of the flow. So different geometry, different condition is all going to affect how much turbulent viscosity is. And here in particular, I'm just assuming in this particular case, it is a linear function of the distance to the wall. Qualitatively, this is actually a very convenient and often pretty accurate description of turbulence. And it is basically saying that, okay, so if my distance to the wall is equal to a tenth of the h is, or b, right? So let me just take both cases to be h. So if it's a tenth of h, then the turbulent viscosity or the mixing due to the movement of large portions of a fluid is as much as laminar or molecular viscosity. But when I'm further away, when my d is greater than a tenth of h, then turbulent mixing dominates, right? Is higher than molecular mixing. All right. And I want you to sketch qualitatively the velocity profile for both cases. Now, mu is not a constant. It's a function of d. All right. In this case, d is either y or h minus y. So if y is less than half h or y is greater than half h, right? And in this case, d is equal to either y or 2h minus y. If y is less than h, y is greater or equal to h. All right, so please form pairs, come up and try to figure out how the boundary layer profile is going to be different. Now we have turbulence helping with mixing. All right. still we're assuming the tau is going to be now mu plus mu t, so times dv dy. All right. Yeah. You know what we're doing here?
So is the main difference with LES, you're only resolving like 80% of the large eddies?
Resolving really X%, right? But like the really whatever eddy you resolve is mesh.
And the eddies are simulated using the kinetic energy, and like I guess the energy dissipation from what's on the molecular state.
Yeah, so like
Oh, not in terms of this, but
what we're doing is similar to ranks, right? So
Yeah.
basically it's modeling the effect of turbulence, but not resolving all the eddies. Like the LDS this is resolving the outstanding eddies. Also the non-resolved are still modeled.
So try the same kind of equations I went through earlier in this class, and then figure out what is the difference of maybe let's work on the first one first, right? First one doesn't have a dx. Yeah, so these are two different cases. It'll be easier to work on the first one first, right? The first one doesn't have any pressure gradient. There is only viscous force. All right.
So basically, it's just a little square. Faster.
Also, by the way, you don't have to work out the closed form. You only need to sketch what it looks like. So working out the exact equation may be too much math, but like if you can look at the equation and figure out how the profile looks like, that's enough.
Oh, didn't you say something like we have to redraw this, right? Oh, because this line here, right, is straight because E X Y.
Again, I recommend starting with the control volume approach, right? So if you draw a control volume, that will help you figure out how basically the balance of forces,
This one looks like this.
right? Then start to write equations on what the forces are.
Plus the square was negative. Negative. And it was counting down. I don't know how that's counting down, but if we have to redraw them, like what they look like now. Oh, wow. So maybe they look different somehow. I'm just can I do it? I just don't do it. Is it T?
So this guy has exactly the same method.
Yeah.
Small other
Maybe
things.
put like UT in here. So maybe because in this case, that just
Yeah. One recommendation I have is not focus so much on equations, but focus more on what they look like, what the functions. If you draw the functions, what they would look like.
oh,
Right.
so this line is just v of x, right? So
Critical thing is that they have strengths no matter where they are. Yeah, so that's right. So the key thing is that
oh, I was trying to think, but like in the other one, this one's not. This whole thing is so maybe this changes.
Yeah, I wrote the equations to illustrate the.
So mine just changed to be with also now.
and we could claim that y was the same for all the y's. Because how is the same, u is also the same.
You know, I would say it's like yeah.
Now in this case,
But then
how is how still the same?
the turbulent stuff makes it greater. This is hard.
That's why I was saying like start with forward. How is the viscous force per area on top of the
Answer the question.
yeah, how still has to be like no matter what y you are looking at. But now in the on the equivalent case you have really something.
That's amazing. Number one.
How is it
Case two.
and
Sometimes we get this stuff right. Sorry.
yeah.
So now for this one. I would say it's like
So how is still the same?
like this is now faster.
Yeah. So okay, so what you use here is how is the constant, right? But can you still say y as a result? Y is the constant? Yeah.
Wait, but what is you know what that's X. You're saying this is also maybe not change.
In the laminar case,
I don't understand it.
how does not equal to y? As a result,
Oh, I'm just fully making this off the fact that he said when it's more. Oh, I didn't think it looked like that. Yeah. I thought it meant it would look like more like how the back. This part I would think would get faster. There it would get faster because of the turbulence shit. Because like it's converting momentum. Yeah. So then it would just kind of flatten this and curve out a bit. Yeah. Like it just kind of looks a little flatter, maybe. So like this is still just as fast. This is now faster. Okay, maybe.
but this thing doesn't. It's not a constant.
Maybe you're right. It looks more
Y
fast.
is 8 times.
Oh, it is.
Yes. So if you can qualitatively draw what y looks like as a function of y, that will help you know how you
Valid.
at the moment.
Where is the like the only one? Like
Yeah, we need to develop.
Since this is actually difficult for people, so maybe let me help you with a little bit. So if you do a control volume analysis, similar to our laminar case, tau is going to be a constant, right? So if there is no pressure force, then the viscous force has to balance each other no matter what kind of control volume you draw, right? The bottom and top of the control volume has to have the same tau. Okay, so in our laminar case, when there is no mu t, we concluded from the fact that tau does not depend on y to the fact that dv dy does not depend on y. But in this case, can we still conclude that? No, right? Because there is a mu t, and mu t does depend on y, right? Okay, and we actually gave you how does mu plus mu t depend on y. So from the fact that tau does not depend on y and the mu plus mu t depends on y, you should be able to figure out how does dv dy depend on y. Of course, there is a constant we don't know because tau is a constant, right? Tau doesn't depend on y, but we don't know what constant it is. So, but you can still draw the function, right? How does dv dy look like as a function? And if you know how dv dy looks like as a function, you can pretty much draw how does v look like as a function. Of course, still you don't know the scale, right? Because we don't know what tau is. But if you can draw this as a function and you also know the boundary conditions, right? You know what v0 is, you know what v at h is, then you can pretty much, right, determine the profile. Does it make sense? Yeah, so if some of you start to try to draw what dv dy looks like as a function of y, that will be very helpful.
How is this a function of y? Because d is y is small d again. Y or h minus y. Okay, d is the distance to the nearest wall. So h doesn't change, right? It's changing. Or the first one, this oh, this one? Yeah, this one. But yeah, but that's why I put it like that. But then for this one, well, how do you know this is one? And then I just I look first one. That's what it be. This has a y in it, right? D is either y or h minus y. So pretend d is actually equal to y. Oh yeah, maybe that's what it is. Yeah. Y is similar to y. But pretend it's like this. Then you need to dv over dy. Dy affect this? No, it was just a constant. Yeah, like I was taking derivative of this. Is it this times this derivative? Yeah.
Okay. Yeah, I think let me explain this at the beginning of the next lecture then, because since it seems that there is a little bit conceptual difficulty with this. So let me come back on Wednesday and explain a little bit more about what happens when you have turbulence. All right. Okay. I mean, if you're interested, you can also come to office hour. I can explain to you over there.
Can I ask just one thing?
Yeah.
Like for this case, if you have a small particle, it's not a small, it's a controlled volume.
Yeah.
The force should still be uniform.
Exactly.
Right?
Exactly.
It means that this tau should still be constant. No?
Tau is exactly constant. That's right.
Okay, my group is constant.
Oh, okay. Yeah. Yeah, you're right. Tau is still a constant. Yeah. When there is no pressure gradient, tau has to be a constant.